Complex conjugates. In the previous video, complex numbers, we established that a complex number is a plus bi, where a and b are elements of real numbers and I is the square root of -1. Further to that, we established that I squared is -1 and that a plus bi times a minus bi, a difference of squares, is a squared minus b squared I squared. And I squared being -1 gives you a squared plus b squared. So a plus bi, a minus bi, is a squared plus b squared. Now yes, a plus bi and a minus bi go hand in hand. They are called complex conjugates. And if you get the 1 as the root of the equation, which only has real coefficients, then we know immediately that the complex conjugate is also a root of that equation. Let's have a little reminder first. We did this in the previous video too. Find a quadratic equation with those given roots. Well, any quadratic equation with given roots will have two brackets, x minus, and the given roots. So therefore here we have x minus, and we have the two given roots. Now, the simplest way to multiply that out is to rearrange these, take away the inside bracket, group x minus 3, and you'll see we have a difference of squares where we are now able to eradicate the I. So this is bracket plus 2i, bracket minus 2i, so it gives you bracket squared minus 4i squared. That multiplies out to x squared minus 6x plus 9, and that with I squared being -1 becomes plus 4. So we have an equation. Notice it says a quadratic equation. It's not the only quadratic equation. We could have 2x squared minus 12x plus 26 equals 0. Another example. Now this time we're only told one of the roots, but there we are. They go hand in hand. So if I have -1 minus 4i, then -1 plus 4i must be a root of that equation as well. So we can go through the same procedure as here. Regroup. Now we have a difference of squares. Multiplying out, simplifying, and there is a quadratic equation which has -1 minus 4i as a root. Here we're given two roots of this equation, and we have to find the values of b, c, and d. Well, what we're going to do is we're going to establish three brackets and multiply them out, and then compare to that there. Notice it's quite important that the coefficient of x cubed is 1. So that enables us to find the exact equation. Now, 1 plus I being a root, there we are, hand in hand, means that 1 minus I is also a root. So we have three brackets. Let's deal with these two brackets first, as we've done in the previous screens. Difference of squares, simplifying to there. Now we can multiply out. X multiplies everything and -2 multiplies everything. And that simplifies to that equation there. Now note it's matched x cubed, so therefore we can match exactly b to -4, c to +6, and d to -4. One plus 2i is a root of that equation. Determine m and n and the other roots. Now we're only given one root of that cubic equation, but we've been given two. The old hand in hand. So that means 1 minus 2i is a root. And I'm going to let the third root be p for now, because that means we have our three brackets, x minus p, x minus, x minus. Rearrange, difference of squares, and we now have a quadratic trinomial there with x minus p there. So we now can compare that to that. We're allowed to, because once again this gives you x cubed and that has x cubed. Now we don't have to multiply this whole expression out. What we can do is say, well, there we are, those two must give you the nth term. So therefore minus 5p must give you 15 and p is minus 3. So back that goes into the equation, and now we can either multiply out or equate coefficients. So we've multiplied out, there you are, and that gives us mx squared, 1x squared, nx, negative 1x. So we have the values of m and n. Some exercises to try. There are difference of squares, and there's an equation. The next one, we establish that we have the complex conjugate, so we have minus 2 plus 5i, which means we have minus 2 minus 5i. Rearrange, difference of squares, and we multiply out. Once again here, we have one complex number, so therefore there it is there, x minus, and we have x minus its conjugate. Rearrange, difference of squares, multiply out, and there's our equation. So here we are given two of the roots, which means we have all three of the roots, because 5 minus 2i being a root means that 5 plus 2i is also a root. So we can have x plus 1, x minus 5 minus 2i, and x minus the conjugate, 5 plus 2i. We're going to work with these two brackets first to rearrange, because that gives us our difference of squares here, which simplifies to that equation. Now we can multiply out, and we end up with x cubed minus 9x squared plus 19x plus 29. Well, x cubed is matched, minus 9x squared plus ax squared. A is minus 9. Plus 19x plus bx, so b is 19. Plus 29 plus c, so c is 29. Note that a polynomial equation of degree n has n solutions in the complex number system. Doesn't have to have n solutions in the real number system. Might have some unreal solutions, but in the complex number systems we include any unreal or imaginary solutions. So just as a little matter of interest, it does mean that all polynomial equations of an odd degree must have at least one real solution. Why is that? Well, if we have a complex solution, then there's a conjugate, so they go in pairs. So if we have an odd degree, that means that there's one left over on its own, and it must have a real solution. And that we've already established. And that we've established. That's complex conjugates. So let's do an example. So there we're told x minus 1 is a solution of that equation. Find the equation fully. Now remember, if 1 is a solution, what bracket must that have come from? There we are. If a is a solution of the polynomial equation, then x minus a is a factor of the polynomial. So therefore, 1 is a solution, x minus 1 is a factor of that polynomial. So now we're going to find the quadratic factor by inspection. But as a side note, you can find the quadratic factor by long division instead, and there's the long division sum where there's the quadratic, there's the cubic there, and I've divided by x minus 1, long division, and I end up with x squared minus x plus 7. And lots of people are more comfortable doing it that way, and you're welcome to do it that way. But inspection is faster. X minus 1 times something gives us this equation, well, that expression. Now, we've got to say, well, x times this must give you x cubed. So if we say x cubed divided by x, we must end up with x squared. And the same thing's going to happen with this and the end term there. If we divide negative 7 by negative 1, we get plus 7. So we have an x squared on the one end and plus 7 on the other. The middle is a bit of a mystery. We're not quite sure. So we'll call that k for now. Now what we're going to do is we're going to compare. We're not going to multiply this totally out. We could multiply this totally out and then compare to that. But we don't need to. What I'm going to do is I'm going to multiply x by kx and negative 1 by x squared, because both of those gives us an x squared term. So kx squared and negative x squared, well, there's the x squared term there, negative 2x squared, which means that negative x squared and kx squared must give you minus 2x squared. And that enables us to find k. K is negative 1. Now we have our quadratic. Notice, there we are, that goes instead of the k. So we have x squared minus x plus 7. And that's the same as what we had when we did the long division. So now we can solve. Using quadratic formula, so there are our 3 roots of that equation. Let's look at another one. Solve that for x. Now, previously, we're told one of the solutions. But in this next one, we're not even told one of the solutions. So we're going to use trial and error. We're going to say, well, let's try to find the first solution. And remember, the first solution, we just substituted a value to find something that makes it true. And if we substitute 1, it doesn't work, not equal to 0. Negative 1 doesn't work, not equal to 0. Substituting 2, we get it equal to 0, which means 2 is a root of that equation. It is a solution. Now, from here, if a is a solution, x minus a is a factor. So therefore, if 2 is a solution, x minus 2 is a factor. So we've gone straight to there. Notice x cubed to give you x cubed, and minus 34 must be minus 2 times plus 17. Now we're doing by inspection. Kx squared and minus 2x squared, they're the x squared terms from that product, must be minus 7x squared. And that gives us k equal to negative 5. So now we have the quadratic factor, and we can use quadratic formula to solve that. There we are. Next example. So we're given one root is negative 1 minus I, and we have to solve that equation. Well, first thing we're going to do is to go to there and say, well, if negative 1 minus I is a factor, then negative 1 plus I must also be a factor. So I'm going to establish the quadratic factor linked to that. So we're going to multiply them out. Same pattern, rearrange, now difference of squares, simplify, and we get x squared plus 2x plus 2. So there is our quadratic factor. Now to determine what's left, I'm going to divide that into that. I'm not going to use inspection. It can get quite complex involving simultaneous equations now. Let's do a division sum. Notice I've taken that there it is there. I've divided by that, and this section isn't to teach you the long division. There is a video earlier, much earlier in my video series, which actually shows you how to do long division. But there we are, we have 2x squared minus 3x minus 2 is the answer to that long division. Which means, therefore, that when we have that, we've ended up with that. So now all we have to do is solve that. We have the solutions to that, and this factorizes to there. So we now know our three solutions. That, and the 2 from that bracket. Some exercises to try. First case, quadratic formula. In this one, we're going to have to do that trial and error. And we find if we substitute 1, it gives us 0, which means x minus 1 is a factor. Now we can do that by inspection, by comparing the x squared terms, where we have kx squared and minus x squared being equal to 3x squared. Gives us k equal to 4. We can substitute back into the equation. Now we need to solve that one. It'll have to be by quadratic formula. And there are full solutions. Number 4, once again, trial and error. And we find that negative 3 will give us a solution, which means x plus 3 is a factor. And we're going to do the same procedure. Equate the x squared terms. Kx squared plus 3x squared is equal to x squared. Gives us k equal to negative 2. Now we can substitute negative 2 in and use quadratic formula. Number 5, knowing that one root is 2 plus 7i, we have our complex conjugates, therefore 2 minus 7i must be a solution. And we're going to find that quadratic factor. There we are. Now we need to find the other quadratic factor, because this is x to the 4 here, so we'll use long division. And that gives us 6x squared minus 7x minus 3. Let's solve that one. And we have two answers by factorizing. And there are full solutions now for that equation.